Hi, everybody. Welcome to the Extreme Performance Series. Today's session is on performance best practices, where we're going to be channeling our inner Monster VM, our inner Melvin the Monster VM, and learning more about the art of performance. But first, quickly, we're happy to introduce this year at VMworld, VMware's cross-cloud services for all applications. We encourage you to learn more about these set of services that we're launching here at VMworld. And lastly, our disclaimer. So what are we going to talk about today? Well, first we're going to talk about AMD and how AMD's architecture has forced an evolution in the vSphere software stack. Then I'm going to turn it over to Valentin to talk about some CPU usage and utilization information. And lastly, going to squeeze in a lightning round around some network health troubleshooting as well, too. So we got a very full agenda for everybody today. So who am I? My name is Mark Aktimachuk, better known as Mark A. I work as a performance engineer here at VMware. I've worked in industry from applications all the way down to infrastructure, and performance is really that art of pulling it all together. I am a VCDX, work with customers on a daily basis, publish white papers, and happy to share with you any of the performance knowledge I have. Valentin?
Thank you, Mark. My name is Valentin. I work in support, have been with VMware for a little bit over 12 years now. And performance and resource management is what I do. And I'm happy to talk here because it's a nice change from only seeing these things when they break, but also talk about them when they work as they're intended. So our session today is built on the performance best practices document. And we will always encourage you to download and read that because that has everything. And we cannot cover everything here because we only have 1 hour. If we would even cover just 3 pages of that, then you would be bored out of your mind after 20 minutes. So read that on your own time, and we'll focus on some topics that are related to the performance best practices. If you want to see more, we have sessions across the years that cover multiple different topics. There's a little bit of repetition, but we have at least 1 or 2 topics that change every single year. And you can use the via.vmware or vmw.com link shortener to access these sessions. With that being said, let me give it back to Mark for AMD and vSphere.
Great, thanks, Valentin. So how many of us can remember back in the day when AMD launched their Opteron series processors and virtualization was just starting to get some traction in the market, kind of the early 2000s. It was an amazing set of technology. It was amazing to see what had happened. Now, certainly there's been a massive set of evolution in processors since then. And so let's talk about that a little bit here. So when we start with the basic constructs, we have a socket, right? And a socket contained a number of CPU cores. And that socket was locally connected to memory. And this is what we would use and put the hypervisor on. So we invented or built, CPU-sched. So the domain of the socket is where the CPU scheduler works. It decides what services to run on what cores, migrations that may need to occur, right? And does the time sharing and the hypervisor. Now, what was interesting about the design of this is that really the last level cache domain really equaled the NUMA domain. So a socket was those 2 constructs were the same. Now, if we added a second socket to a server, right, we can see on the other side, we have the same set of constructs, right? The NUMA domain being the second socket, which equaled the last level cache, and right, CPU scheduler in there decided what moved around. Now we had 2 sets of memory, each local to those sockets. So if we needed to access remote memory, there was a different access latency. So it was non-uniform, right? Or hence NUMA. So the idea here was we needed another piece of code called the NUMA scheduler. So CPU scheduler works within the NUMA domain, and again, deciding what runs where. NUMA scheduler decides what runs across the NUMA domains, and if we need to do placement or migration of workloads across those 2. So they work together hand in hand, and those were the 2 layers. This has been the typical architecture that we've been working, in the x86 space for a number of years now. So what's happened? What's the evolution we want to talk about today? AMD EPIC drops. And basically, the architecture there now breaks that assumption that the last level cache domain and the NUMA domain were the same. So let's take a look at what that means. So now within a socket, we have a number of last level cache domains, and each of them has proximity to a set of physical cores. And what this creates for us now is this idea of non-uniform cache access, right? Where we have cores in proximity to last level cache, but because there are multiple sets of them within the socket, now we can start to take a look at, well, execution isn't going to be, or access to the cache will not be uniform all the time. That's the big change for the AMD EPIC architecture. So we needed a bit of an evolution, right? Remember, this was the domain of the CPU scheduler. It's deciding where to go, but it was based and built off the premise that those two constructs equaled each other. So let's push the evolution towards this idea of an LLC scheduler now. So the question that gets asked, right? And this is why we're here to talk about it today. How do I get the best performance on ESXi with AMD? So let's take a bit of a step back here too and talk about some of the configuration. So as the sockets became available from AMD here, there was a BIOS setting of interest that the community started to use to change the presentation of the socket. And the reason this was done was potentially for some performance. So let's kind of walk through what those look like. And really the setting that's most important here is the NUMA nodes per socket. Right. So as we talked about, each socket contains a lot of CCDs, a lot of memory controllers. And when it's set to NPS 1, the full socket is configured as a single NUMA domain. So memory is interleaved across all 8 channels, right? And one NUMA node is exposed to the OS, or the hypervisor in this case. You could also configure this, again, at the BIOS layer to say NPS 2, where we would take that socket and break it into 2 NUMA domains. So here, the memory for each domain is interleaved across half the sets of channels, so just 4, right? And the hypervisor guest OS is going to see 2 NUMA nodes. One step further, NPS 4 means we'll take that socket and break it into 4 individual NUMA nodes. That's what's exposed. And now each of these NUMA nodes has 2 controllers to interleave the memory across. So as we think about taking this and shrinking this down, the question is, well, why? Well, because part of the construct here where we talked about the non-uniform cache access, by breaking these into smaller NUMA nodes, we tended to be able to push together and limit how far we had to go with some of that cache, right? So there was some advantage in doing that. But as we can see here, remember, NUMA scheduler, its job was to move things between NUMA nodes. So now within the actual socket, NUMA scheduler and CPU scheduler are doing work. And that's starting to grow in the amount of effort and energy spent managing the workloads within the socket here. So while this was done for specific purposes, certain workloads may benefit from it, we can start to see here the complexity of what setting should I choose? Does my workload apply to that particular setting? How much energy are we expending between our sets of services to manage all the scheduling here? And let's make it even more complex. So there was another setting available here, which was called the CCX, or the core complex as NUMA, right? Which is basically the L3 boundary. And what that would look like on the socket here, again, remember that each compute die was actually 2 core complexes with 4 cores and their own LLC. So if we apply the CCX as NUMA, we would actually get 16 individual NUMA domains now. And so while that proximity, right? So now that the core complex and the cores and the LLC seem to be all aligned and tight, 16 NUMA domains presented from a socket is an excessive configuration, right? So again, there was a spectrum where workloads may benefit from these, but what's really important here is that all of these BIOS modes impact performance. And if they're not set right or done right, or you understand your workload, they can have devastating side effects for performance. So the challenge here now is, well, what do we do? How do we simplify all this? Thank you for the background, Mark. I get it. What is VMware going to do to simplify my world? Dun, 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 dun. introducing vSphere 7U2 now with the LLC scheduler. So let's look at this through a little bit of example. So what happens prior to the introduction of our LLCSched, right? And this is a simplified view, right? We're going to assume this is NPS 1. And let's start up a VM. So we got a 4 vCPU VM. And we can see that one of the vCPUs is placed in each of the CCXs across the CCDs. Let's start up another VM. Oh, interesting. So the way it's distributed was within a CCD, but across CCXs. And let's start up an 8-way VM. Oh, interesting how it's been split here as well. Now, prior to LLCSched, right, the idea of making the LLC as a boundary, remember, we worked within the NUMA node as the MPS. So here we can see that CPU scheduler was doing a good job moving things around as we needed, but we can see that we really can't take advantage of that last level cache, right? We're getting that non-uniform cache access here. So while CPU scheduler did its job, let's call this suboptimal for the architecture of AMD. So introducing the idea of understanding these constructs and the LLC now as a boundary. So let's start up a 4 vCPU VM, right? CPU scheduler or LLC scheduler now understands that, right? So it's picked the vCPUs, it's mapped them to physical cores within that same boundary. So we get uniform cache access and the VM fit. Let's start up another VM, right? 4 vCPUs as well. Same thing happens. We actually distributed that to a different CCD to, again, for reasons that we're looking at utilization and taking that into consideration where we start this placement. What about if we build an 8-way VM? What does it look like? Well, the 8-way VM we can see is distributed here across 2 CCDs, 2 core complexes. And so it was divided into these smaller relation nodes, or we can call them LLC clients. So the 8 vCPUs still are distributed against the minimum number of LLC clients that are required. Again, now this looks far simpler. This looks like optimal placement. This looks like the ability to take advantage of that non-uniform cache access better. This was the big design change in executing how we schedule within this AMD architecture. So here, again, that idea of breaking down the relational nodes 1 and 2 for that single VM. And the same thing will happen as we continue to power more and more on. So let's take a look at that a little further. How is the wide VM broken down? So a 16 CPU VM, right? If we look at the physical architecture on the bottom, we have 2 NUMA nodes. So of course, the VM will be broken into 2 NUMA clients, right? 8 vCPUs in each one. Then those 8 vCPUs will be broken further into their LLC clients or relation nodes. And then those individual constructs will be scheduled onto the physical CPUs, right, on the proper NUMA node, on the proper core complex, abiding by that LLC boundary. So that's kind of how things will come apart and be scheduled down. Now, there's a lot of interesting stuff kind of around this. This was an excellent evolution. And the one thing we want to call out here is that vSphere is the first known hypervisor that fully understands and implements the EPYC architecture and is aware of how to use it and consume it. Right? This provides better load balancing and improved cache locality. And the thing, again, we wanted to strive to do was not worry about all these advanced settings. We wanted close to optimal performance out of the box without having to configure a bunch of things. And for us, that means the NPS setting is 1, presenting that whole socket as a single NUMA node, and making sure that the CCX's NUMA is disabled. So here's a white paper put together by many engineering folks in the company with a lot more detail you can go check out. Again, here's the quick link on the top that will go into a little more detail around it. But we're very excited to be able to introduce excellent support and excellent performance now on the improved AMD architecture that we weren't able to really offer before 7.0 U2. And with that, I'm going to turn it over to Valentin here.
Thank you very much, Mark. And we're going to talk about CPU usage and utilization, what that means for a host and for a VM, and why there are two different metrics and what they do. So let me start out by showing you something all of you have seen before, or maybe have seen before, maybe not, our beloved vSphere client. And when you're looking at the consumed CPU and consumed memory of this particular example, while I can't see you, because again, recorded, I can feel while you're watching this that you're shifting uncomfortably in your seats. I'm here to tell you that maybe, just maybe, this actually is fine, right? Maybe this isn't just quite yet a reason to be highly alert. Because what we want to do today is talk about whether CPU usage really is that final frontier, whether 100% really is that final frontier. Okay, so the CPU usage at the host level is accounted at the nominal frequency and without SMT, so without hyperthreading. Nominal frequency means the base frequency of the CPU, right? If we want to further define that, the overall 100% level of host CPU usage is the nominal frequency multiplied by the number of cores. Not multiplied by the number of pCPUs, not multiple times the maximum potential frequency, the nominal frequency. Only the base frequency counts. And we all know that is definitely not the end all of CPU frequencies. So let's talk about nominal or base frequency a little bit more. Basically, it's what's on the box, right? Here we have a packaging for an E5-2620V3, which is coincidentally the same CPU I have in my lab and where we'll show you the data from. And basically, the slides are put together relatively fast, and then I need about 2 weeks to find the pictures that fit my lab. So I couldn't find one that actually had the text on here, but we all know what we're talking about. It's an E5-2620V3, same CPU I have, and it says 2.4 gigahertz printed on the CPU. That's the nominal / base frequency. So you can also check that. You can check that in many different places, whether it's ESX CLI hardware. I like to get it out of VSISH CPU model name. And that frequency, by the way, that's in the CPU model name, that is not the actual frequency. That is just a string that's saved in the microcode of the CPU. It's called a brand string. That is not the actual frequency. The actual frequency is actually measured by ESXi when it boots up, and it's a little bit more precise. So this is not quite 2.4 gigahertz. It's actually 2399, right? And well, actually, it's a lot more if you round up, but there is not much missing. But the actual frequency is a lot more precise. So this CPU, right, has turbo boost, and turbo boost is dynamic overclocking of the frequency of the CPU, and you can either overclock all of the cores at the same time, or if you want to overclock just a few but higher, you have to deep idle some of these CPUs. So if you look at some of our previous sessions, you will hear us talking ad nauseum about power management and turbo boost and how it all works. But the takeaway today is that there are different frequencies depending on how many CPUs are active. Active means not in a deep C state, not just any C state, not C1, but in a deep C state. So that also means that all of the cores, there is a turbo boost level for all cores when none of them are idle or in a deep C state. And on this particular host, I have 24 pCPUs, 12 cores. And again, it's Intel, so 2 LLCs and 2 NUMA, where these two still match. And when I'm looking at ESXtop, and I all encourage you to try out ESXtop, and I'm looking at the actual versus measured performance, which is the frequency, above nominal frequency, I can see it is 108%. If I want to calculate what that ratio is, right, we can actually use tools like awk and printf for that. I can see that the nominal frequency and the max all-core frequency, right, is 8%. So what we see on the ESXi host here and what we see in the Intel documentation actually matches up. Now, the link in the bottom right corner links you to the spec of the Intel document. It looks a little bit odd because it is in their download portal, and I think that link might be generated. Not sure whether it works, but if you search for the terms that you see on the left-hand side, you should be able to find it regardless. But the takeaway here is you can use the document or ESXtop to find the maximum all-core frequency. So let me maybe look at more modern CPUs, because this is the one we're going to use for the tests, but there are bigger, better CPUs out of there. So this is for some fairly recent CPUs. So this is Cascade Lake. And what you can see is there's a lot more cores, right? So here we have columns going all the way to 28. So what I did is I took that data, right? And I put it into a table, and I calculated based on the max all-core frequency, meaning the turbo boost that can be executed on all cores, so no matter whether any cores are deep idle or not. I calculated that, calculated the ratio, and basically sorted by how many extra cores, just based on the nominal frequency you get. And at the top, you see that 8276 CPU, right? Where the nominal frequency is 2.2 and the max all-core frequency is 3 gigahertz. So basically, if that runs at its all-core turbo boost frequency, you're getting an additional 10 cores of capacity. Imagine that, right? So, and I sorted by those, and I just picked the first one because it has the most extreme values. So I'm going to explain what's happening based on that. By the way, maximum all-core frequency, it is not a common acronym. I'm not sure whether I made that up. I don't think it is mentioned in the literature anywhere. But when we talk about MACF, the max all-core frequency, that is what we're referring to. The maximum turbo boost frequency without having any cores in a deep C state. So basically the same frequency that you would have if you would run at a maximum performance or low latency kind of BIOS power management setting, because usually that enables turbo boost, but disables all P states, disables deep C states, and so on. So if you don't want to search the docs, and I already showed it, but I wanted to have it in an extra slide just to underline what you can do. You can start ESXtop. You can press P for the power view. You can press F for fields, F for AMPerf. You press enter again, and you're in the power view. And here, the AMPerf is actually the percentage above the nominal frequency that you're running. So in this particular case, I have the same CPU. My actual CPUs are running 8% faster than the nominal frequency at all times. Now, we could talk about turbo boost here and how guaranteed it is. Now, in theory, turbo boost is opportunistic, meaning there is a chance that you don't get turbo boost. But that really is just down to whether you have adequate cooling and heat removal in your data center. If everything is working fine and there is no alerts peeping up in your BMCs, then for most instances, you will have that max all-core turbo boost frequency at all times. It basically behaves like the nominal frequency. I have yet to see that it actually doesn't. And really, that is sometimes in environments where there is no adequate cooling, or whether there are BIOS bugs or configuration issues like energy capping, but it really isn't all that different from the nominal frequency pre-turbo boost. So let's look at that big bad 8276. I choose Intel because we already talked enough about AMD today. And here we can see that it says 2.2 gigahertz on the CPU, right? Now, if you can go to Wikichip, which I really like this website. It has a nice overview of the different frequencies and different active number of cores. It also shows the AVX2 and AVX512 frequencies. Basically, these CPUs run at different frequencies depending on the type of instructions they execute. If you're executing a lot of AVX instructions, floating point, then it will actually run slower. But we're not going to look at that. We're just going to refer to the simple, straightforward normal execution. So here, nominal frequency is 2.2, max all-core frequency is 3 gigahertz. Now, the maximum frequency for just 2 cores active is 4 gigahertz, right? So if you have deep C states enabled and you're running a balanced ESXi power policy, if you only had 2 cores active, then those would run at 4 gigahertz. But if you, let's say, have a high performance policy, all of the CPUs will run at 3 gigahertz. So that means you get an additional 36 capacity compared to nominal frequency, and it's 82% faster if you would use a balanced policy with maximum turbo boost for some CPUs, right? Now, but I don't have a CPU like that. I'm pretty sure VMware has it somewhere, but the access that I have to my lab, the easiest thing that I can work with is the 2.4 gigahertz 2620. And here, if we look back at the documentation, we can see 2.6 gigahertz. That'll give me a modest 8% additional capacity when I run at max all-core frequencies, and it gives me 33% additional speed if I want to use deep C states, if I want to optimize for a max turbo boost. So this brings me to a question that is asked very often. So you're saying that nominal frequency or maximum host usage is nominal frequency multiplied by the number of cores. Isn't that what is reservable? Or is reservable what is capacity? And the answer is yes and no, right? To some extent, they're the same thing, but it doesn't quite work that way. Let me make a small excursion to how resource pools work in ESXi. The host object, right, owns all the resources. And on ESXi, right, it's resource pools all the way down. Even if you don't use resource pools, everything from ESXi is actually structured in resource pools. Under the host pool, we have a system pool, a Vim pool, which houses like the logger, hostd, VPXA, if IO filters, and we have user. And under user is where you would create your resource pools on ESXi or via vCenter. Now, below system, for example, there are many more pools, and it really goes down fairly far, right? There's multiple levels of structure, and how resource pools work for the user, they also work for ESXi internally, but you usually don't see anything of that because it's pre-configured, it's predetermined. So these consumers, these resource pools, they actually ask for resources from their parent resource pools, the same way that you have learned it for how resource pools work on a user configurable level. And what vCenter shows you actually, if you click on a cluster with multiple hosts, all of the sum of the resources the host can manage is the cluster total capacity. And you always noted that that didn't match the total reservable capacity because, again, system and Vim and IO filters are reserving capacity before they're actually given to the user. So what you see in the user pool is what is left over, what ESXi is reserving before that. Now, comparatively, that's relatively little to what the actual capacity of the host is, but there's always something reserved already to ensure the proper functioning of the ESXi host. So if you go to the user pool, right, that is actually called total reservation capacity, and that will be less than what's available under the host. And under the user pool, ESXi will create resource pools. They're just called pool with a number based on the instantiation. So whenever you move a VM in a resource pool onto a host, it'll create that resource pool. If there hasn't been a VM already that was part of that resource pool. And basically it maps the same structure that you see in the vSphere client. Within those pool, you have VMs, and those VMs are made up of different worlds as well. But this is taking it already a little bit further than I wanted to. Now, how can you check that out? Now, this is by no means exhaustive, but if you want to see what the structure is, and if you want to look at some of the tools available to you on ESXi, because this session is partly about giving you some benefit in your day-to-day, but also allowing you to figure stuff out and play with some of the tools that we're using to display some of that information. And one of those is SCHED. And when we look at groups, and by the way, that -z parameter there, where you can specify the columns, is new in 7.0 update 2. If you're not on 7.0 update 2, you would have to use awk to print the relevant columns, or just use dash capital S and have a very wide monitor. But the interesting columns are here. It's the name, it's the group ID, it's the parent. So it's the group ID, it's the name, it's the parent group ID. It's the minimum, which is the reservation. It's the max, which is the limit, and the reserved megahertz and the available megahertz. So here you can actually look at the resource pool structure on the ESXi host. I know that used to be available in the very old C# client, but we removed that part of the UI because too many people played with it and changed the settings where they shouldn't have. So sadly, we had to get rid of it, but you can still see the same thing nowadays if you use CLI tools. Now, you should, again, those are only looking at things. You're not actually changing anything. This is more for discovery rather than for editing. Now, if we look at the zero group, which is the host group, we see that there is a certain amount of CPU reserved and CPU unreserved, right? So if we add that together, right, and divide it by 12, which is the number of cores, what is the value that we would expect? Based on what we're saying, that capacity is very similar to what is reservable at the host level. Ultimately, before anything else reserves something, The answer, of course, is the nominal frequency of our CPU, which is 2,400 megahertz. Now we can also look at different groups here. We're looking at the user group, at the user pool, and where we see the capacity, the CPU unreserved. And look at the columns in SCHED as well. We're looking at this. Currently, there is no VM, no resource pool, no reservation under the user pool, meaning there is no VM or resource pool configured. And you see what is unreserved and available on that particular host. You can see the same thing in SCHED. But that was enough of a detour. Let's get back to the actual metrics after this slide. So many people ask, hey, okay, this is reservation, but reservation isn't consumption. Reservation isn't usage. I know ESXi reserves some resources, but where can I see how much it's using, right? I don't have a percentage sys counter like I have in Linux to see what it's actually doing. Well, it's not the best comparison. It's definitely lacking. But you can look at the individual high-level resource pool, CPU, and memory usage in the advanced performance charts. Now, many of you probably haven't explored that, but if you select system, and then you select resource CPU usage, for example, you can check the high-level resource pool and see what they're actually consuming on ESXi. Now, that is usually way below what they're reserving, but it's there, and now you know. Okay, let's get back to host and VM usage and utilization, and why, first of all, the metrics are different, and also why it looks so different for a VM and for a host. Now, again, remind yourself that we have a 2-socket system, 12 cores, and 24 pCPUs in total, right? That is what we're working off. Now, what I like to do is I like to show what I did. And I like you to play around with that and maybe experiment and do it on your own. And you don't have to read that. Please don't read that little script there. But what that does, it is basically outputting VMX options to create a VM that has the same size as the host, because we want every vCPU to be matched to a pCPU. And hyperthreading is enabled on this particular host. We set the right cores per socket. We set the right maximum per virtual node. So basically, the VM that we're creating exactly matches the host, including the vCPUs to pCPUs. So the reasoning for that is so that we trigger something within the guest that if we run something on vCPU 0, then pCPU 0 will also be busy. If we run something on vCPU 21, pCPU 21 will be busy. Right, and that just helps us being deterministic and having predictable outcomes, and to show us how these metrics are working. What I also like to do is I like to disable co-stop. Now, the reason why I'm doing this is because I'm lazy and I only have one large VM that exactly matches the host. I'm not creating 24 individual VMs that I then control remotely. I have just one large VM, and by default, co-stop is enabled, meaning if something else is running and there's a little bit of ready or a little bit of VM wait, right, then some of the vCPUs will be co-stopped, and that then messes up the result. So I just disable it because I don't care about correctness. I don't care about preemption of anything within the guest, because this is just a stress test, right? This is not a benchmark. I don't care about performance. I just want to use those vCPUs and those pCPUs, and I want to put some load on it. I don't care about the results, really. Besides that, it's not idle. Right, so that's why I'm disabling co-stop here. You shouldn't really do that in production, because co-scat still gives you, usually has a return on investment when it comes to performance, to prevent some of the issues that you could see if you don't have it. For example, but let's not go there and keep co-scat maybe for a separate day and separate topic. So one more is the power stabilizer. So this is assuming that your ESXi host is configured according to best practices and power management best practices. And we really do welcome you to refer to some of our earlier sessions where we talk all about that. So basically, the assumption is that you can control P states and deep C states from the guest operating system. Everything else could be configured similar to the max performance profile, but we really want you or need to control the P states to disable turbo boost and to disable deep C states. So even if you want to run into high performance policy, it's always nice for it to be able to be configured by ESXi, because then you don't have to reboot, you don't have to mess with the BIOS. And basically running this here, I'm setting the max frequency and the min frequency to the P state below the maximum P state. So that means I basically on Intel, right? AMD, it works a little bit different. But on Intel, I can run without turbo boost, but still at the maximum nominal frequency. So basically, I'm removing turbo boost from the equation. Yes, I talked about turbo boost before. For this particular example, I'm not going to mention it because it's only 8% on my setup. So it's not really worth it to show it to you. I just want to talk about the difference in presentation for usage and utilization for hyperthreading. And then later on, we bring turbo boost back into it. So this disables turbo boost, disables deep C states, so that we have nice deterministic metrics for our CPU usage. And then there's one last script here. This basically creates load within the guest. So this you run in Linux where you have stress and G install. And what I'm doing here basically is I'm creating 12 threads on every second vCPU, right? Remember that that two pCPUs are one core, meaning two threads are next to each other, underneath is a core, right? So I'm creating 12 vCPUs for every second pCPU, meaning initially when this loads up, it'll put some load on all 12 cores over 12 vCPUs out of the 24 available. And then every few minutes, it'll create another CPU, another thread, and put that onto the same core as another thread. So basically, we're starting with full core load, and then we're ramping up the threads. How does that look? Remember that 12 vCPUs initially, and then one additional one every few minutes. And if we look at the advanced performance charts for the host, you can immediately see that CPU usage, host usage, right? And core utilization, which is the same for us in this example, and I get into it a little bit later, usage and core utilization is the same. It's completely maxed out, right? Why? Because we already have 12 threads running at full speed, but we still have 12 additional threads available. And look at that. Utilization, when we start off, is only at 50%. Usage is 100 and utilization is only at 50. We can start 12 additional threads and utilization goes up at a 40. I mean, it goes up per vCPU. So that's interesting. So usage is already completely full. Utilization isn't. So utilization is basically at 50% when we only utilize 50% of those vCPUs. Now, why is that? So let's dive into those metrics very, very briefly, right? Usage is a qualitative metric, right? It includes, for example, nominal frequency. We want to show you the approximate throughput that you have with that metric. So it includes frequency, which we eliminated because I said no turbo boost, no frequency scaling. So usage is pretty much similar to core utilization here. Now, utilization only means whether a pCPU is running an idle thread or not. If something is executing on a pCPU, on a thread, right? Whether we run the idle thread or not, that is utilization, nothing else. So that means it actually doesn't really care at what frequency something is running. If something is running on one or the other, that on one pCPU, that is utilization. Core utilization, again, refers to the cores. So it actually checks whether one or both are utilizing. Only if both hypertwins, if the hypertwin, right, is completely idle, you will have no core utilization. If thread one or the other one is utilized, you will have core utilization. If both are utilized, you have core utilization. So there actually is no differentiation between running or two running, but either or has to be running for you to see core utilization. And what does that mean? Well, that since it does not really care about frequency, core utilization tracks whether at least one thread of the core is fully utilized. So it kind of includes the nominal frequency capacity, right? If we're assuming, right, that utilization stays at 50%, meaning only half of the cores, and this is assuming a theoretical workload that is perfectly distributed across all pCPUs, and that doesn't happen, right? Mark already talked about NUMA nodes, about last level cache, and there's all kinds of intrinsic stuff going on. But from a very remote, very high level ideal distribution, right? That core utilization metric is tracking whether the core, one thread or two threads are fully utilized. And assuming that's only one thread of the core, it will reach 100%, right? It can reach 100% while utilization is still at 50%. So it really shows you once you max out that turbo boost frequencies, right? I hope that kind of made sense. But let's maybe look at it from a per vCPU perspective. If you have not watched one of those sessions when we talked about vCPU usage accounting. Really do review those. If that picture looks familiar, that's great. If not, let me not waste too much time on that, because what we really only want to cover is why utilization can be different than used from a vCPU perspective. So all kinds of things can reduce use. That is overlap, meaning interrupts, can be hyperthreading, that can be frequency scaling. Now, usage can also be larger than run, which is, again, the vCPU term for utilization, basically whether vCPU is scheduled on a PCP or not. But there's many things that can reduce it or increase it, which is turbo boost. Only one thing that can increase it, which is turbo boost, and actually also sys, if something is doing I/O on behalf of the VM. But we really just care about hyperthreading, right? And everything is defined, again, nominal frequency times number of cores. So if you use hyperthreading, right, 2 threads together on a single core, we assume the total benefit is 25%. 25% on top of 100 is 125. 125 divided by 2 is 62.5. So the maximum non-turbo boost usage of a vCPU that is utilized at 100%, so running at 1%, is only 62.5%. So let's look at that in the actual vSphere client, right? Here you can see that same example, 12 cores, 12 vCPUs are immediately utilized. And you see that there's 2 different charts here. There is used in millisecond and run in millisecond, and there is usage in percent. And everything, what I really just want to show you is that used in millisecond and usage in percent have the same progression. They immediately go to 50%, but then the usage doesn't really climb, right? So your VM, if your VM has more vCPUs than PCPUs, and you're using hyperthreading, more vCPUs than cores, and you're using hyperthreading and eliminating turbo boost, that VM would never be able to reach 100% CPU usage. It will always be below because, again, usage is reduced when you run. What we charge for usage is reduced if you run on the same core. Now, utilization, so used here, as you can see, is increasing exactly as it does on the host because you're utilizing more vCPUs. The vCPUs are not idle anymore. They're actually utilized, but you're not getting the same usage out of them because ESXi for you accounts for hyperthreading. It doesn't double your potential performance, right? So hence why you're seeing that this actually moves differently. And if you look at run here, the black line, note that you shouldn't use the right-hand scale, which is percentage. That is just for the usage counter. Again, it's in milliseconds. I could have used VRUBs here to make it easier, but not everyone has VRUBs installed. So I'm just using these representatively. But I think the point is clear here that utilization is just whether something is running or not. And usage is qualitative, defined cores times nominal frequency. So if we put these next to each other, right, we can see how it does look like, right? From a host perspective, at the first second, right, the whole host is already completely used. Whereas you look at the VM, it only has 50% usage, right? When we only have 12 cores busy. Because again, the assumption here for the VM is cores times nominal frequency, and you have more vCPUs than you have cores. So again, you cannot reach that. I know I'm repeating myself here, but it's a really important point to remember when you look at these different objects and you want to see what the utilization is. And very often we had these, hey, I have this VM, it's a monster VM, and it has less usage than the host. How come? Well, the reason is using hyperthreading. And sometimes when people switch over, for example, from different hypervisors or from different operating systems, they're confused because our usage counter is not really that industry. I mean, there are different counters that measure the same thing. But for example, the top level metrics on Hyper-V or on Linux are actually a lot closer to utilization than they are to usage. Whereas our top level metric is usage because we want to be very performance conservative. We want to actually show you that your performance probably will change once you go past that 100% point. Now, I'm also here today to tell you that for some workloads, depending on your max all-core frequency, it probably will not change all that much once you move 100% usage. You might actually be able to go to 100% core utilization until you see some of the impact of hyperthreading. Now, all of this is idealized. Hyperthreading is going to work in some way or another all the time. And because there are different scheduling domains on an ESXi host, the ESXi host is not one big domain. It is separated into NUMA domains. It is separated into last level cache domains, and the scheduler is placing workloads depending on relation and utilization. But assuming a perfect spread, right, you usually can max out core utilization before you would feel the per thread impact of hyperthreading. So let me put it this way, right? If you look at the metrics, you will reach 100% CPU usage first, but then you still have all of your max all core frequency turbo boost capacity to go. Once you reach 100%, then you still have utilization. Now this looks like turbo boost and hyperthreading give you like more than 3 times the resources. That is not the case. This is just how the metrics look. Because as soon as you reach the end of core utilization, and if you're looking at throughput, utilization will ramp up a lot faster than your throughput would. Because again, it's not the same running on the same core, right? Because there's shared resources. So if you're actually looking at throughput, it looks a lot closer to this. Once you reach 100% usage, you have a good bit of core utilization, and that depends on your CPU and what your max all-core frequency is. And then you still have a good bit of hyperthreading. And we calculate 15 to 35%. Our own scheduler assumes 25. Now, the summary here really is that ESXi is capable of running and scheduling VMs and enabling high density, but it is very careful. The metric that it shows you are usually very conservative, and there is usually a lot more afterwards. Let's take this example, right? You know the saying that there's a second stomach for cake. I'm not quite sure which country it originated from, but it's similar here, right? The 100% CPU usage is like a good solid dinner with entrees and everything, right? But then turbo boost is kind of the cake that you can still put on top. And then you can still manage to get 1 or 2 espresso done after that. And that kind of is hyperthreading. So there is more after you reach that 100% in the UI. And it really pays to look at some of the other metrics that are available, even if they're not front and center. So it's not quite as straightforward, right? Because these metrics are not available except in real time. So if you want that in vCenter, it's kind of complicated to configure that. In VROPS, they're also not defined manually, but you can enable the collection of these metrics and you can build dashboards with them. We're still trying to look into how we can improve the visibility to basically show you all that capacity that you have in your hosts and not mislead you for you to think that 100% really is the end. It is a very conservative, very safe end. Now, many of the alarms still rely on CPU usage, right? So if you want to run your environment a little bit more efficient, a little bit denser, you might want to disable these alarms or change the metrics for alarms depending on what other products you use and how you want to run your environment. With that being said, let me hand it back to Mark for a lightning round at the end on how to network health check, specifically for how you identify world CPU capping for relevant nodes.
Great, thank you, Valentin. So I hope everybody kind of took that away as a very interesting look at those counters, because again, it shows that, you know, within the interfaces there, like Valentin demonstrated up front, high utilization doesn't necessarily mean you're out of performance yet. And so important to understand those, use those, and look for things like, you know, contention as well too. So that said, minds melted around those. Let's shift direction here a little bit and talk about the network. So one of the things that I find interesting, and a couple of things I've worked for recently, is you know, some high throughput applications. And you get the question of, well, is the network the bottleneck? Is the network the limit? And so I wanted to just spend a couple of moments on some limited scenarios here on that idea of, you know, health checking the network stack, you know, in particular around high throughput. So this methodology can kind of apply to everywhere else, but what I kind of want to bring up around it here is that, remember, when we're looking at the network, it could be a sender or a receiver side scenario, right? So to check the health of that, we want to make sure that we're looking at both. It can't just be one side or the other. So again, think of this as the bigger picture. Look at both sides. And then ask yourself the question, okay, what network thread is burning pCPU at 100%? So remember that when we're using the virtualized network drivers like VMXNet 3, the vSphere host is doing work on behalf of that guest. So it's not just all what's happening in the guest VM. We are also doing things around that. And these are the worlds we're talking about. These are the worlds that are receiving from the physical layers and that are helping pass that up and out of the VMs, right? So this is the set of worlds we want to look at. And so how do we do that? So the best way to do this is through yet another good tool. As Valentin noted, right, here's another example of something you can go look at and look at some of the outputs and see what you can see in it. That's netstats. So netstats in the example command here really takes a snapshot, right? So it goes through 2 seconds worth of time and will deliver you kind of the results of what happened over that window. Now we can use something like a grep on that and look for used. And what that's going to show us is the thread utilization, as well as some contention values. And I have an example of that you'll be able to see shortly. And what we want to look for here is that none of these network worlds are at high utilization or saturation. If that's the case, we certainly know that we can't push or pull anymore through there. The other thing we can do too is look at counters there called RxEPS for receive errors and TXEPS for transmit errors. And that approximates basically drops, where we want to make sure that everything we've sent or received has made it up and down the stack. So if we use the netstats to take a look at those two values, kind of what we're doing is we're saying, yes, we're at saturation, or no, we're not. Yes, we're delivering everything or receiving everything, or no, we're not. So again, using this kind of tool and looking at a couple of snapshots helps us kind of isolate whether or not the network stack may be a bottleneck, may require some different tuning or some adjustments. And again, wildly, we're going very quick here. That will help you kind of, again, give it a clean bill of health or look towards some optimal settings. And now the last layer we need to think about here is, again, right back at that physical NIC. And so here we can use something like the ESX CLI and apply that towards the particular VM-NIC interface. And that's going to give us the low-level stats, again, from that layer. So you have to, again, remember the picture of network where we have the physical layer, we have the work we're doing on behalf of in between, and then we also have in-guest, right? So it can be the fact we could deliver everything in-guest, but we can't drain it in-guest fast enough using some of its processes. So think about the layers as we go through this. And again, the eyes have built more of a focus on the middle layer here around work we're doing on behalf of the VM. So shouting out to the couple of different world types we're interested in here. So there's the net worlds, and these are the transmit worlds that are associated with the VMs. And then there's the pull worlds, and these are the receive worlds that are basically associated with the physical layers and up. So when we look at those utilizations, again, using netstats, if we see a net world, a transmit world, let's call saturation, anything above 90% gets busy there. There's a couple of things we can do. Now, I use the idea of explore the CTX per device setting, because there are many reasons we may or may not want to adjust it depending off of the number of virtual interfaces and the number of flows. But this is how we would deal with a transmit problem out of a VM typically. We're going to need more interfaces. We're going to have to split the flows. We're going to have to add more threads per transmit. And so this, again, is the tunable we could look at to adjust for that. Again, go away, Google that, some great resources on it. And I have a couple more resources we can use as well too. Now, if netstats is showing that some of the pull worlds may be at the saturation level, then here again, I throw out the idea of, explore the PNIC features. This allows us to actually use more receive queues. So we can distribute the receive across more threads in order to do some of that. And this is, again, how we would kind of eliminate, pull world bottlenecks. So here's an example of the output of netstats. And again, I've taken snapshots that are interesting here. If you go and run it, you'll see that it spits out a lot more information. So you can use your favorite tool of choice to parse out what you need. But the idea here is I have a receive and a transmit side, and we look at used. So used is, that thread. How much of a physical core is being used? In this example here, 5.7%, right? So we know that thread is not near saturation. Interesting enough, we also see ready time and co-stop time for it, right? So these are worlds we schedule around the VMs. We don't want contention necessarily on those worlds either. especially for very latency sensitive things. So we can see a little bit further to the right, this was VM-0. This was a poll world for it. We can see it's not highly used and there's not a lot of scheduling contention around it. Transmit side, let's look, the VM's actually transmitting something, 17.29% used. So something's going out, and we can see again, a little bit further to the right, that that's a net world for the VM. But again, not much scheduling contention at all either. So with a quick snapshot and a look at this, we could say, well, no, there's not a readily obvious saturation point for these worlds in and out of the VMs. Now, here's again an example if we were to look for potential drops, or we classify these as some of the errors. So if we take a VM here, we can look at the RxEPS or the TXEPS, and both being 0, that's good. That means everything is being received and handed off and passed up, So there's no errors, there's no missing packets, there's nothing being dropped at the virtual layers where we're doing work on behalf of the guest. So again, another clean bill of health to be able to show something like that as you collaborate with your network folks. Now, this again, we could spend a whole day on networking, and we just can't fit it into the session here. So do look at the performance best practices guides. We have some more information around it in there. And if you do have the Tech Plus Pass for VMworld here, Valentina and I are going to be hosting an Extreme Performance Series Performance Bootcamp, where we'll be talking more about that as well. So please do check that out. And lastly, for hands-on labs, we have an introduction to vSphere performance that does talk about network and network configurations, and there's some great information in that HOL. The guides, the lab guides for it, are really forms of documentation on how to look for things and settings and stuff like that. So again, a couple of great resources for how to explore the network and understanding the network better within the virtual layers. So lastly, we want to leave you with a few resources, because Valentina and I aren't always there, stand up in front of you and answer questions. It's a little bit harder to get through support. So how can you better your performance art, your skills, and stuff like that? So VMware Tech Papers, and here's the link. This is where we publish a lot of great guidance, where the best practices guides go, where that AMD Epic Performance guide goes. And you can see that if you were to click on just the performance category itself, we have 248 white papers published. Now, lots of those are probably very old, so you're only going to roll back in time a little ways here, but this is an often unknown site to go get those white papers, to learn more about each of the white papers, because again, they detail experiments, configurations, and results. And so you can really learn a lot by going through those. The performance engineering team also has a blog we like to call Vroom. And this is where we publish a lot of results for experimentation we're doing, or insight into tools we use, or testing of new stacks or pieces of software and stuff like that. And you get some great tips and tricks on how to configure things as well. So definitely use this as a landing site to go see what's current with the team, what we're working on, what we're publishing, and what we're seeing. It's a great source, again, for performance information, tools, and tricks. And lastly, as Valentina kind of pointed out earlier, we continue to strive year over year to deliver new content at VMworld here. So go back and check the old stuff. We're not re-rinsing and replaying the same information. Go back to the previous VMworlds, because there's a lot of great sessions, both in the Extreme Performance series, but as well as everything within our software portfolio. So do a search for performance. You'll get a lot of great information that comes up here as well. And so with that, we want to thank you for taking time today. We hope you learned some new tools, tips, and tricks as well, that you're honing your performance skills. Performance makes you excited. It's an amazing space here. You can be very confident with the vSphere platform. And so thank you for your time today. And please remember to fill out your surveys. Thanks so much for joining us today.